After the prototype phase, the process enters the characterization and models phase. During this phase, the prototype seals will undergo characterization that will feed our physics behavior models and our DDDR surface textures library. This step will help determine the final texture needed for the customer use case. Within the boundaries defined, the design of experiments technique is applied to effectively plan and conduct the experiments in optimal conditions. The non-textured metal plates can be manufactured according to strict quality requirements. They will then be laser engraved following the DDDR surface texture used for our prototype mold and seal to be coated with the mold release formula if necessary. After the uncured rubber material is prepared, the demolding process is analyzed experimentally at laboratory level with laser-textured mold samples. The experimental setup intends to replicate mold transference with the capability of measuring demolding forces in the most unfavorable situation. A universal testing machine is used and specific test fixtures inside a climatic chamber are employed. During the procedure, the material is transferred from the transference chamber to the mold cavity through a transference piston. Finally, the rubber sample is extracted from the mold and the demolding force, which corresponds to its specific microtexture and rubber compound, is measured. The experimental and numerical mechanical characterization of the rubber is done to feed the numerical modeling of the friction behavior, where the material properties have to be numerically described. To that end, tensile and compression tests are executed once the cured rubber material is prepared in the form of rubber slabs and buttons. A dynamic mechanical analysis is also done to describe the dynamic behavior. On the other hand, the tensile and compression tests are simulated for the different experimental cases using patch test models, which consider real test conditions of temperature and strain rate. The material parameters that feed the constitutive model are fitted so the experimental and numerical stress versus strain curves match in the strain range of interest for this kind of sealing applications. First, the V-ring seal to be tested is mounted on the specimen holder of the test rig. Both the seal and the counter surface are lubricated with the help of a brush. The fitted width, which determines the contact pressure between the seal and the counter surface, is adapted to the operating condition to be investigated. A running-in procedure, which is performed at the highest velocity to be analyzed, is performed to condition the rubber sample and ensure constant fluid film thickness in the dynamic contact. Finally, the actual friction measurements are performed, whose target value is the frictional torque as a function of the fitted width and the rotational speed of the seal. The friction measurement procedure of the U-cup rod seals starts with the assembly of the seal in the cap of the pneumatic cylinder. The inner side of the seal, which is in dynamic contact with the rod, is lubricated with the help of a brush. A cover plate is mounted on the pneumatic cylinder to secure the position of the seal. The lubricant is also applied to the rod surface. After the cylinder pressure has been adjusted via a pressure control valve, similar to the V-ring seals, a running-in procedure is performed to condition the seals and ensure a constant fluid thickness. Afterwards, the dynamic friction between the U-cup seals and the rod is measured as a function of the cylinder pressure and the rod velocity. The numerical modeling of the friction behavior in the dynamic contact of surface textured seals is essential for the prediction of the friction level and the understanding of the underlying friction conditions. In order to compute the friction in both boundary, mixed, and hydrodynamic lubrication regimes, a coupled contact mechanics and fluid mechanics simulation procedure is used. The simulation steps are indicated in the red boxes, while the transfer parameters from one to the next simulation step are shown in the blue boxes. Initially, the seal, fluid, and operating conditions like the seal geometry, the velocity, and the dimple textures are specified. Some of the input parameters, as the seal surface roughness and the fluid viscosity, are based on experimental measurements which were performed in a previous step. Afterwards, a static contact mechanics and deformation analysis of the untextured seal is performed by finite element analysis. The output parameters of these simulations are the contact length, Lx, and the contact pressure level, PdC smooth, between the seal and the countersurface. These values are forwarded to the contact mechanics analysis, which is based on the Greenwood and Williamson contact model, in order to determine an initial fluid film height, h. The following fluid mechanics analysis utilizes the Reynolds equation for the identification of the fluid pressure, Pf. Both the static contact pressure, PdC smooth, and the fluid pressure, Pf, are coupled by an equilibrium of forces in order to calculate the dynamic contact pressure, Pc, which is entered to the Greenwood and Williamson contact model again. This process is repeated in an iteration loop until the fluid film height, h, is converged. In the final step, the friction coefficient in the dynamic seal contact is determined with the help of the previously calculated fluid and contact pressure, as well as the fluid film height, h. The decisive output parameter of the model is the coefficient of friction, which is determined as function of the operating conditions and the surface texture. The resulting friction coefficients are further processed in the reduced order model of our holistic design software. At this stage of the workflow, data have been obtained from friction and demolding characterization, and these data are analyzed with reduced order modeling to be plugged to the holistic design software. In particular, reduced order modeling is a numerical method for multivariable problem simplification, which reduces dramatically the computational cost required for solving complex numerical models and synthesizing experimental data. Our approach aims at describing and hence predicting a system's behavior through a mathematical approximation by preserving its main characteristics and physical parameters. Regarding friction behavior, the software is based on a complex mixed friction model and experiments with real seals, which are simplified through reduced order modeling. In particular, the geometrical parameters that characterize the microcavities are the diameter, the distance, and the depth, and the parameters of the operational conditions are the pressure and the velocity. As a result, the simple platform allows the user to obtain real-time friction reduction prediction for a given set of parameters and the optimum combination to maximize friction reduction. On the other hand, the presence of microprotrusions in the mold may render the demolding difficult, so this process is analyzed experimentally and the knowledge is integrated into the tool. To that end, the experimental data are simplified again with reduced order modeling, and the geometrical parameters taken into account are the diameter, the distance, and the depth. In this case, the tool allows the user to analyze, from a qualitative standpoint, the demolding forces for a specific set of parameters and to determine which is the most appropriate texture in terms of demolding forces. The MouldTex optimizer integrates several modules: an area for the definition of the input parameters, a module for real-time friction reduction prediction, and a module for real-time demolding forces estimation. In all cases, the results can be visualized in different ways: through 2D or 3D graphics, or through plain numerical values. Moreover, an optimization module provides the optimum solution for your system, and a summary shows the quality of the computed reduced order model.